Have you ever looked up at the night sky, letting your eyes adjust to the darkness and wondered what secrets it holds? You see stars, planets, maybe the moon, brilliant points of light scattered across the vast black canvas above us. But what about the things you don't see? The sky hides more than it reveals. Our universe is filled with invisible forces and objects, phenomena that shape our world, yet remain hidden from our eyes. Light travels in waves, but only a tiny slice is visible to us. There are waves all around, radio waves, X-rays, microwaves passing through us, through the Earth, unnoticed. In human conflict, a similar idea took hold. What if you could make a machine invisible, not to our eyes, but to enemy sensors? Imagine a plane that could slip through the most advanced defenses, unseen and unheard. This is the dream of stealth technology, the science of not being seen, of vanishing in plain sight. The goal? Create vehicles that slip through defenses undetected, moving like shadows across enemy lines. Stealth is about manipulating how we're seen, by light, radio waves, and sound, bending the rules of detection, and rewriting the playbook of modern warfare. Radar changed warfare forever, letting us spot planes from miles away, even in total darkness or thick clouds. Stealth is the counter-revolution, a cloak that makes the metal bird disappear from the radar screen, turning the hunter into the hunted. It tips the balance, making information or its absence the ultimate weapon. In the fog of war, what you can't see can hurt you the most. But how do you make a jet vanish? It's not one trick, but a symphony of science, engineering, and innovation working together. Shape, materials, heat, every detail matters, from the angle of a wing to the paint on the surface. And even electronic emissions must be controlled, because every signal is a potential giveaway. Stealth is a profound challenge of physics and engineering, demanding constant innovation and relentless testing. It's about becoming a ghost in the machine, completing missions before the enemy even knows you're there, rewriting the rules of engagement. This isn't magic, it's clever manipulation of nature's laws, using science to outwit technology. Join me as we pull back the curtain on the secret science of stealth and discover the hidden world behind the invisible cloak. Let's explore how physics becomes the ultimate tool of evasion and how invisibility is engineered, not imagined. Imagine you're in a pitch-black room, holding a flashlight, searching for a hidden mirror. The darkness is complete, and the only way to find what you're looking for is by carefully sweeping the beam across the space, hoping for a glint of reflection. When your light finally hits the mirror, it bounces straight back at you, bright and unmistakable. This is exactly how radar waves behave when they strike a surface, like a plane in the sky. Traditional aircraft, with their rounded, curved surfaces, act like giant mirrors in the sky, sending radar waves right back to the radar station, making them easy to spot. Stealth aircraft, however, are designed differently. They use flat, sharply angled panels to deflect radar energy away from the source, scattering the waves in multiple directions and making the aircraft nearly invisible to detection. The F-117 Nighthawk, for example, looked almost alien, a collection of flat triangles and sharp edges. Its unique shape was engineered specifically to scatter radar energy in every direction except back to the enemy. Early stealth technology relied on these simple, flat surfaces because computers at the time could only handle basic calculations for how radar would reflect. Today, modern jets like the F-22 Raptor and B-2 Spirit bomber use smooth, flowing curves. Thanks to powerful computers, designers can now calculate complex shapes that are both stealthy and aerodynamic. These advanced shapes allow jets to slip through the air efficiently while still evading radar detection, combining stealth with speed and maneuverability. But the core principle remains the same. Never reflect radar energy back to its source. Instead, send it somewhere else, anywhere but back to the radar. Every panel, every angle, and every curve is meticulously calculated to minimize the chance of detection, turning the aircraft into a puzzle of geometry. It's geometry as a weapon, transforming the aircraft into a kind of black hole for radio waves, swallowing up signals and leaving little trace behind. Today's supercomputers allow engineers to create even more sophisticated and efficient designs, pushing the boundaries of what's possible in stealth technology. The result? Aircraft that are not only hard to see, but also incredibly hard to catch. Ghosts in the sky, slipping past enemy defenses. Stealth always starts with shape, but it doesn't end there. Materials, coatings, and even the way the plane flies all play a role. The battle to remain unseen is fought with every line, every curve, and every detail, each one a calculated move in the chess game of aerial warfare. The ultimate goal: make the radar echo vanish, sending it harmlessly away and leaving the aircraft undetected. The shape of a stealth aircraft is only part of the story when it comes to evading detection. Imagine if you could absorb radar waves instead of just deflecting them away. This is where the magic happens. Stealth aircraft are equipped with special coatings known as radar absorbent materials, or RAM, which play a crucial role. These coatings are not merely paints, they are intricate composites that transform radar energy into heat, rendering it harmless. Take iron ball paint, for instance. It contains tiny spheres that vibrate and dissipate radar energy effectively. The outcome is remarkable. Radar waves are absorbed, not reflected, making the aircraft nearly invisible to radar. Engineers meticulously layer various types of RAM to ensure absorption across a broad spectrum of radar frequencies. The most radar-reflective parts, such as wing edges and engine inlets, receive extra attention, sometimes integrating RAM directly into the structure. However, this magical skin is both delicate and costly to maintain. Even a minor scratch can compromise the aircraft's stealth capabilities, so maintenance is extremely meticulous and precise. Ground crews employ specialized tools and work in climate-controlled hangars to preserve the integrity of the coating. Stealth technology is not just about design, it requires constant and careful maintenance to remain effective. This cloak of invisibility is powerful, yet it remains fragile and requires diligent care. Every inch of the aircraft contributes to its overall invisibility, making each part essential. Absorbing radar waves is just as crucial as deflecting them, ensuring the aircraft remains undetected. The science of stealth is a delicate balance of advanced materials and innovative design, constantly evolving to meet new challenges. Shape and RAM work together to shrink an aircraft's radar cross-section, or RCS, its electronic size. A stealth jet aims for an RCS as small as a marble, making it nearly invisible to radar. This lets it fly much closer to enemy sensors before being detected. Details matter. Cockpit canopies are coated with thin films, engine blades are hidden in S-shaped ducts, and weapons are carried inside. Even seams and screws are sealed to keep surfaces smooth. When weapons bays open, it's a brief moment of vulnerability. Every component is designed to minimize reflection. The result? A holistic approach where every part contributes to invisibility. Stealth is about making the aircraft a ghost in the radar's gaze. The tiniest detail can make all the difference. Radar isn't the only way to find an aircraft. Heat and sound give you away too. Jet engines produce intense heat, a beacon for infrared sensors. Stealth aircraft mix hot exhaust with cool air and use special nozzles to spread and hide the heat. These nozzles are often placed on top, shielding them from ground-based detectors. Sound is another clue. Stealth jets use quieter engines and smooth shapes to reduce noise. Even the paint matters. Special shades of gray or black help blend into the sky. Some research explores skins that can change color to match the background. The goal: minimize every signature: heat, sound, and even visual. True stealth means being a whisper in a world of sensors. Every emission is managed, every detail counts. The science of stealth is about more than radar. It's about vanishing from every kind of detection. The ultimate goal: total low observability. Passive stealth, shape and materials, is just the start. Modern stealth jets use electronic countermeasures, or ECM, to actively jam and deceive enemy radar. Active jamming floods enemy screens with noise, hiding the aircraft's faint echo. Deception techniques create false targets, confusing defenders with phantom blips. The most advanced systems use sensor fusion, combining radar, infrared, and threat detectors to build a complete picture of the battle space. The aircraft's computer automatically deploys the best mix of stealth and countermeasures. It's a digital chess match, anticipating and countering enemy moves in real time. Stealth is as much about brains as it is about invisibility. The digital side is the invisible shield behind the invisible plane. In the end, it's a battle of wits and technology. The ghost in the machine is always adapting. Stealth isn't new. Camouflage and silent movement have been used for centuries. But technological stealth began with the F-117 Nighthawk, developed in secret during the Cold War. Its first real test was the Gulf War, where F-117s struck key targets in Baghdad undetected, changing warfare forever. Stealth aircraft flew a tiny fraction of missions, but hit a huge share of strategic targets, all without losses. The B-2 Spirit bomber followed, showing global reach and strategic surprise. Stealth became the crown jewel of air power, sparking a new arms race for invisibility. The battle to see, and not be seen, now shapes the future of conflict. Stealth isn't a magic cloak. It has limits. The biggest is cost. Stealth aircraft are expensive to build and maintain, so only a few can be fielded. Stealth works best against high-frequency radars, but low-frequency radars can sometimes spot them. These radars can't guide missiles, but they can alert defenders to search with other sensors. The cat-and-mouse game between stealth and detection never ends. New ideas like multi-static radar and advanced infrared sensors are always emerging. Networks of computers can link sensors to spot even faint signatures. There's no perfect, unbreakable technology. Every advantage is temporary in this endless duel. Invisibility is always a fleeting edge. What's next for stealth? The future is adaptive, intelligent, and multispectral. Imagine aircraft skins that change properties in real time to counter any radar frequency, using metamaterials that bend waves around the plane. Future jets may look conventional, with active skins managing their signature on the fly. Stealth will expand to cover heat, visual, and electronic signatures with new cooling and decoy technologies. Unmanned drones will push stealth even further, freed from human limitations. The dance between detection and evasion will keep driving innovation. The quest for invisibility, born from physics, will shape tomorrow's conflicts. The science of not being seen is only just beginning.